Hello and welcome to this webinar on machine learning in R, hosted to you by Mango Solutions. My name is Joe Russell. I'm one of the data scientists here at Mango, and I'm going to be walking you through this webinar today. So without further ado, I'll just go over the agenda for today's webinar. So to begin with, I'll just give you a brief overview about Mango, what we do, and then we'll go and look at what machine learning actually is, before diving headfirst straight into how we actually perform machine learning within R. So as I said, firstly, a little bit about Mango. Mango are a company that empower organizations to make informed decisions using sophisticated analytic techniques such as AI and machine learning. And we do this to deliver data-driven value to companies. And there's three kind of key areas that we do this through. This is firstly through data science, which can be through consulting or app development, which is where the machine learning mainly comes under. But also we provide to our customers data engineering. So this can be analytical infrastructure, which enables these machine learning projects to come to fruition, as well as DevOps and modernization. And then finally, we also offer data products, which involves app development, validation, and testing. So let's go and jump in to learn about what actually is machine learning. So machine learning is a scientific study of algorithms and statistical models that computer systems use to perform a specific task without using explicit instructions, relying instead on patterns and inference. It is seen as a kind of a subset of artificial intelligence, which is a word that the media kind of like to throw around a lot these days. So if you take the example of Pac-Man, the ghosts in this example move with a look of intelligence. They turn around corners and occasionally change direction. They even have their own personalities, and they are all like diligently pre-programmed rules. Machine learning will aim to explicitly program as little as possible, and instead the computer will learn from experience. So as an example for the DeepMind project, which you might have heard of, and they took this to the extreme when it programmed its systems to learn old computer games from nothing but the pixels on the screen, to score and experience from millions and millions of games. Microsoft cracked MS Pac-Man with a team of deep learning startup, which can be found if you search Google. These methods used deep learning, which is in fact a subset of machine learning. But this is only a small component of machine learning. Deep learning is a form of machine learning that has been growing enormously in popularity in the last decade. And this is mainly because the extra flexibility that comes with it is at the price of requiring a large amount of data, a large amount of processing power, the likes of which has only been available in the last decade or so. And so here we've got a nice quote from R. Samuel in 1959 on what machine learning is. So he says that the field of study that gives computers the ability to learn without being explicitly programmed. And here R. Samuel is listed as being the AI pioneer, and is said to have coined the phrase machine learning. This is not to say that no programming is involved. Instead, the program in some way writes parts of itself, learning decision boundaries, fitting lines, etc., based on the data that you feed it. Some people might think that machine learning and statistics are quite similar, and they do share a lot of methods and theory. But mostly the difference between them is the priorities that they have. So statistics typically is usually tasked with fitting a model to the data that sufficiently explains the observed behavior. It is quite important that we understand why things happen, and we would like a model that we can understand and draw inferences from. Machine learning, on the other hand, is usually tasked with making predictions on unseen data. The correctness of this model is much more important than predictive power. It is common for the same person to perform both types of analysis. It all depends on the project's priorities. So without further ado, let's kind of have a look at machine learning within R. So R kind of comes with a few kind of, well, it comes with lots of different packages, but there are the base packages that it comes with for machine learning are called NNet, standing for neural net, and RPart. But there are many, many others available from R's central repository called CRAN. These include, but not limited to, E1071, Random Forest, XGBoost, and GLMNet. Many of these machine learning methods derive from statistics. Others have independently developed, and the biggest difference between the two is what is trying to be achieved. So as well as just packages, R has a number of external machine learning platforms that it connects to. So there are a number of projects that have created powerful open source machine learning libraries, and all of these, or many of these, are available to our user without having to actually leave their R session. So these include H2O, Spark, TensorFlow, and Keras. And there's also a number of framework packages that are available to the R user. These aim to unify the interface to which all the various algorithms can be used from. In addition, they streamline the machine learning process with pre-processing, partitioning, and evaluation functions. The key packages here are the Caret package, standing for classification and regression training. This is the most established of the framework packages. It works well with all other major machine learning packages and provides rich features for pre-processing, partitioning, and evaluation. The MLR package is a framework for machine learning experiments in R. This is a direct competitor to Caret, created by a large team of developers, which has a clean interface and is easily extended. Caret and MLR are equivalent in terms of functionality. And then the final framework package that we're actually going to be looking at today is the Tidy Models framework. This is a collection of packages very similar to the Tidyverse, if you've heard of that, which is designed to work together as a flexible and easily extendable framework within the Tidyverse. This is a new toolset, and the interface is still establishing. Work is led by Max Kuhn, who also wrote the Caret package. So it's expected that the tools will continue to integrate well with Caret. Great. So the first thing to do, we're going to talk about getting our data into the right shape. So in machine learning, we refer to our dataset as a data matrix. Typically, this is organized with our variables as columns and our observations as the rows. All values in the matrix are assumed to be numeric. Therefore, before we can fit any models, we must make sure that we have the right type of variables in the right shape. We can divide our variables into three categories. Firstly, the target. This column contains the variables that we are trying to predict. In statistical terminology, you might call this our response variable. Secondly, we have our features. These contain, hopefully, the predictive information that will be used during our project. In statistical terminology, you might refer to these as the explanatory variables or the covariates. And finally, we have something called the identifiers, here listed as our row ID. These often arrive with your input data, but we cannot use identifiers in our model fitting because they are unique to each row and cannot possibly be generalized. So here the ID column is unique to each row, and it's just kind of random number. It's no logic behind how these have been defined. So this is the kind of the data matrix. When we refer to this, is just this is what we refer to. Now, when we're performing machine learning, there's two kind of types of prediction. Specifically, when we're performing supervised learning, which we're looking at in this webinar, there'll be two types of prediction. The first being regression. Regression prediction is problems where the target variable that we mentioned before, a variable is numeric. So for example, this could be something such as height or weight. But we could also have the classification prediction, and this is where the target variable is categorical. Classification can be either binary or multi-class. So you could have something such as whether someone is male or female, or you could have a number of categorical values that you're trying to predict. So once you've decided on your type of prediction, you need to perform your exploratory data analysis, often shortened to EDA. And this is a really important stage, an extensive topic. At this stage, you want to look and get a feel about your data. How is it distributed? Are any features highly correlated? Are any obvious transformations being taken, such as logs? How does each feature relate to the target? And this stage, we're not aiming to solve the problem we've been tasked to solve, but instead we're just taking a little visual dive into what our data contains to help kind of set the scene to what we might expect. So to do this, we're going to have a little demonstration within our studio. So I'm going to jump over to our studio. And we're talking about getting in shape here. So we're going to have a summary of the topics we've just discussed. So the first thing to do is to load in the tidyverse package. And this is going to load in all the packages that we need to perform our EDA and this first look at our data set. And for this webinar, we're going to be looking at the data set on breast cancer. So let's read that in using this read CSV function, and let's have a little look. So we can see here that we have a data set of 569 variables with 22 columns. And if we want to see a target variable that we're going to be predicting, which is this class, this is either whether someone's breast cancer is malignant or benign. We're going to be trying to predict whether this based on these 20 other variables. So if we look at the class, the class of this target variable, we can see that R is treating this as a character, and this is because it is just a string. So if let's have a look at our data set. We can see that this is just a string of either malignant or benign. Now, if we left this as is, R would just treat this as a string and would not relate all these malignant cases to be the same variable. So we need to convert this to be a factor, and we're going to do that using the mutate function from dplyr. Running this, we can now perform check the class of our target variable again, and we can see that we have now updated the class to be a factor. And because of this, we can now see the levels of our class. So we can see that in this case, we have both the levels benign and malignant. Okay, so that's great. So now let's actually have a look. Let's count how many cases there are of both benign and malignant cancers in our data set. In doing so, we use the count function from dplyr, and we can see that we have 357 rows that are benign and another 212 that are malignant. So in this case, we are going to try and predict the number of the positive case when people are malignant. And so if we look again at our levels, when we call the levels, we can see that the first level is benign and the second level is malignant. And this is because by default, R creates factors alphanumerically, and so because B begins before M, is put benign as the first level. But as we're looking for the positive case, we want malignant to be our first level. So we need to relevel our factor. And we can do this using the FCT relevel function from the forecast package. And running this, we can now see that our levels have been updated so that malignant is the first level. So great, so now we have our target variable in the right format. We're ready to go and use this. Let's turn our attention to the features, to the things that we're going to try and use to predict this target variable. So I'm going to run the function glimpse our data. And we can see here that what it's done is produce a really quick summary of all the columns in our data set. So we can see here that we have our ID, we have our target, which is the factor now, but we also have a number of these numeric columns called mean radius, mean texture, etc., etc., relating to the breast cancer. So this is great because we need our data matrix, all the features of our data matrix to be numeric, so we don't have to change any of these in the current format. So now let's turn our attention to the EDA. So first, we're just going to attempt to see what's actually in our data, how much is missing. And to do this, we're going to just do a sum on whether any values are NA. And if we run this, we can see that we actually have 12 cells in our data, our NA. And if we run this on a column by column basis, we can see that these are kind of scattered about the data. So we have one in mean texture, one in mean concavity, excuse me, etc., etc. So we might want to get rid of these. So let's try, we can do that using the drop NA function. So currently our data set has 569 rows and 22 columns. Let's drop all the NA values and then let's see the dimensions again. And now we can see that we've got the same number of columns, but we've lost 4 of our rows. And these rows relate to the rows where any NA is occurring. So where any of these values, the columns where these values are here, the rows have been dropped. Now if we check again the number of NA values, we can see that this is now 0. Great, so let's have a kind of a visual jump into our data set. And to do this, first we're going to create kind of a correlation matrix. So what we're doing here is we're gathering all of the feature columns, and we're going to create a plot, a density plot, and wrap this, so create a subplot for each based on the keys that we have produced. I'm running this. It may take a second. We can see that the relationship between our target variable, our malignant or benigns. We can see a relationship between each of the features that we specified. And we can see here that there seems to be quite a distinct relationship between the two, especially with some of the variables such as mean area. There seems to be quite a distinct difference between the malignant and the benign cases. This is great. We're kind of having a quick look in. We can do some more kind of comparisons. There's a package called ggalley, and this is a really nice function in it called the ggpairs function. And all you need to do is run this. And it kind of produces one of these plots for you. Here we're just performing this on the first 4 columns of our feature. And so you can see here this gives a bit more of a varying types of plots to analyze our data set. So we can see we have some box plots based because of our target is a factor. We can also see we have some correlations and some scatter plots, as well as the densities that we listed before. So this is a really easy way and quick way to get a quick glimpse into our data. We can also use a function from the core plot package called core plot. And all this does is it creates a correlation plot of the variables of features in our data set. So if we zoom in, we can see here that the darker or the larger the point, the more correlated the variables are. And so we can see that here we have a correlation, a strong correlation between the mean smoothness and the worst smoothness, which we might expect. And you can kind of see that there's some kind of some squares, some kind of broken up relationships forming here. Okay, so great. So that's our kind of a quick dive into EDA. You can obviously perform much more analysis and look more closely at these variables. This is kind of a really good way of just jumping in and getting a first look at our data. So to finally to summarize what we've done so far, so we have read in our data, we're going to drop the ID column and we're going to create a factor for our target variable. So this is kind of just summarizing what we've done so far in this step. Great. So next we're going to look at fitting a model. So now that we're in the correct shape and we have some idea what it contains, we are ready to fit a model. Now, machine learning, compared to statistical analysis, is more focused on the ability to make predictions on unseen data rather than explaining the data that you have. So the algorithms used in machine learning are not always very easy to take apart or to understand why they are making the predictions they make. There are other R packages such as Lime or Daleks, which allow you to explain why algorithms are making the predictions they are, but we won't be covering that in this webinar. It is common practice to treat machine learning like running an experiment. We need to build an infrastructure around our models. So when we produce, around the models we produce to test that they are working as expected. This infrastructure is our machine learning workflow. The core workflow is made of three parts. Firstly, splitting the data into a training and test set. Secondly, fitting a model. So we're going to choose an algorithm, e.g. a logistic regression or a decision tree, and we're going to fit this onto our training data. And then finally, we score the model using the fitted model to make predictions to the test set, which we can then compare to the actual values or the ground truth values. So this split fit score is the kind of methodology we are going to follow in this webinar. So let's have a demonstration of this. So we have already prepared our data, and let's get ready to fit a model. So firstly, we need to load in the tidy models package. And this is going to load in all the packages required to perform our workflow. And in this example, if you want to follow along, I'm going to set the seed to 123, just because obviously there's some randomness involved here. So the first thing to do is to split our data. You can do this using the initial split function. And we're going to provide our data set and then provide the proportion that we want to split. So the number here is the proportion that will be in our training data, and the 1 minus this proportion, so 0.25, will be the proportion in our test data. And then we can also define the strata. The strata is to make sure that we kind of keep the number of the ratios of positive, so malignant and benign cases the same between the two data sets, between the training and the test data. So for running this and looking at the BC split, we can see that we have 427 rows in the training data and 142 rows in the test data. And we can access these two data sets using the functions training and testing. So let's run these. And now we have our two data sets in our variables BC train and BC test. So let's check that these the ratios between these two sets are equivalent. So we can do that by just performing a count. And we can see here that in our training data set, we have 159 cases of malignant, 268 of benign. And in our test data set, we have 53 malignant and 89 benign. So these are kind of, if you quickly do the math in your head, these are roughly equivalent. So now we're ready to fit a model. The first thing you need to do when using the tidy models framework is specifying what type of algorithm you're going to be using. So we're going to be using a logistic regression. So we can define that using the logistic reg function. And if we look at this, all this is saying that this is logistic regression model specification. Once we've done this, we can set the engine, and this can be, we can change this to be anything. So this could be a linear model. In this case, we're going to be using a GLM, a generalized linear model. And we just pass our logistic regression that we've just defined into this set engine function. Now that we've done this, we can look at just our logreg object again, and we can see that it's now picked up that our computational engine is a GLM. So now that we have set the engine, we are ready to train our model. So we can pass our logreg object into the function fit, and then we're going to tell it that we are trying to predict the class. So this is our malignant or benign. And we're going to be using all the features available to us in the training data set by specifying this dot. And so running this, we can see that we have now managed to fit a model. And we have a brief summary of the output of this model here. So we have the model coefficients. So you could imagine you want to do this in one step, and doing it as so, we could just run logistic regression, pass it straight into set engine, and then pass that straight into our fit. And doing so, we'll get exactly the same output of our fitted model. So great, we've managed to fit our first model. But now we need to actually test how this model has performed. How well has our model performed predicting data that we haven't seen before? And so there's two different kind of ways you can, for our two different predictions, with classification and regression, the types of performance metrics that you will want to use are different. And so to do this, we're going to need to summarize our predictions as simple metrics, which allows us to compare one model to another. So for our example, we are going to be looking at because it's a classification model, we can look at the accuracy, precision, and recall. And there are numerous other methods, summaries that we can use to compare how well our model has predicted. Which metric you want to use largely depends on what type of analysis you want to perform and how your model is going to be used in production. So let's have a demonstration of how we use these performance metrics, how we calculate these performance metrics. So we have our fitted model, and we're going to try now to predict the values in we're going to try and predict the target values in our test data. So you'll notice that in our fitted model, we have only trained this on our training data sets, but now we're going to try and predict the values in our test data set. To do this, we're going to simply provide a fitted model and the test data set into this predict function. And doing so, we get this data frame called, with only one column in it, called pred class. And you can see here we have a number of predictions of what we have in the data, what our model thinks the target variable is, either malignant or benign, based upon the features in our test data set. Now it's just given us a raw output here, telling us whether it's malignant or benign, but we might actually want to see the probabilities behind each of these calculations. So how sure the model thinks it is that the class is either malignant or benign. And to do that, all we need to do is specify the type argument as prob. And doing so, we can see that for each, so in this case, for case 1, it is 100% sure, almost 100% sure that it is a malignant case, and it is very, very sure that it isn't a benign case. And you can see each of these probability values coming down here. So for row number 5, we can see that it's slightly less likely that it's it thinks it's a malignant case, but it's still pretty sure that it's a malignant case. So that's great. We've got what we think the model is guessing, but we actually need to compare this to the real results now. So we've got this predictions, but we want to compare it to the real things. And to do that, we need to bind this column onto our test data set. And to do that, all we need to do is use the bind cols function. and we are going to select first the class from our test dataset, so the target variable, and then we're also going to bind on the column from our predict function that we provided above. And doing so will provide us with a data frame of predictions. So let's have a look at this. And you can see here that we have the first column, the class, which is the actual values from the test data set. And then the second column here is the predictions that we've made in our data based upon our model. So we can see here that we've actually got them all right, apart from this number 8, because there was an 8 in this column, so it hasn't been able to predict this. So great, so we've got these, we can compare these now, but we need to summarize these to see how well it's done, how many of these has it actually got right. And we can do that using the metrics function. And what we're providing here is we're going to provide this predictions data set that we've just created. We're going to tell it which column is the true, which is the right one, which is, and then which is our estimate, which are the values that we have predicted. And running this, let's have a look. And I can see that it's provided two metrics, both accuracy and kappa, and it's provided an estimate of these two. So we can see here that actually the accuracy for our data set is 96%, which is really, really good. This is a really good model. Whereas a kappa is slightly lower, 92%, but this is still a really strong value. And you might want to kind of the calculations behind these accuracy and kappa values. You can go look into. This is much a similar way when you have false positives and false negatives using a confusion matrix. So you could look at it as so. You could calculate or create a confusion matrix using the conf_mat function. Again, providing our predictions and telling it which is our true, or which are our true values and which are our predictions. And having a look at this confusion matrix, we can see that, okay, we've got 50 where they are malignant and we've got that right, so true positives, and we have 86 true negatives where they're both benign. But then we have 3 cases where we've predicted that we think it's malignant, but it's actually benign, and 2 cases where we predicted benign, but it's actually malignant. So these are our false positives and our false negatives. And if we wanted to extend our metrics, have a look at some more metrics, we could use a summary function on our confusion matrix, and this will give us a list of all the available metrics that we can use to compare. So we can see here we have our accuracy and our kappa. We also have the sensitivity, the specificity, and a number of other values that we can use to compare. So this is how we would actually justify our model. And you can imagine if we fit another model, we could compare these values and see which one it performs better on, and then use that model in our production. So that's great. So we've now fit a model and produced some metrics on how it's performed. So now we are ready to take a kind of step back, kind of look more different, and look at pre-processing. So far, we have done very little to actually change the data within our data set, other than removing the ID column and removing rows containing NA values. This all falls under the initial preparation stage, indicated by the first arrow here, as it occurs before we split the data. Now, a key part of machine learning is called pre-processing, which is performed after splitting the data. At this point, all information within the training set is safe to use, allowing us to perform scaling transformations, imputations, and so on. It's really important not to perform any transformations or imputations before splitting the data, as this will leak some information about the test set into the training set, which will bias our model. Only calculations on an individual row by row basis can be performed during the initial preparation. So we perform pre-processing on our training data set before we fit our model, and then we also perform that pre-processing on our test data set before we evaluate. So let's have a demonstration of how we might do this in R. So again, let's take our data set and read it in. And again, we're going to set the seed to be 123 if you want to follow along. And we're going to, again, split our data set into two, a training set and testing set. And this time we're going to be using a package called the recipes package. The recipe allows us to find some transformations that we're going to apply to our data set to the training data set without applying it to the test data set. And we can define a recipe using the recipe function. Well, what we need to define for the recipe is our target variable and our data set. So we're going to be doing this to the training data set and running this. So we can see our recipe, we just have an output here telling us what our variables are. So we have one outcome variable and 20 predictors. So these are our features. And then on this recipe, we can now define some transformations that we want to perform. So in this example, we're going to be performing a step mean impute. So for all the missing values, so if you remember, we had 4 rows which contain missing values, we're going to impute data. So we're going to take the mean value for each of those columns and impute, replace those NAs with the mean for that column. And we're going to perform that on all the numeric columns in our dataset using this all numeric function. Similarly, we're going to center the data. So we're going to subtract the mean from each of the values, and then we're going to scale it. And this is, can be useful to do because it means that if you have a really outlier value that's really, really large, this can have a massive effect on our data, on the fitting of our model. But if we center and scale it, this outlier, the importance of this outlier will be reduced. So if we perform all of these and we run our new rec impute recipe, we can see that now we have, again, the same number of outcomes and predictors, but this time we have, it says down here, we have mean imputation, we are centering for all numeric, and we're also scaling for all numeric. So great, we have this recipe. Now we need to prepare it, and then we can apply it to our data. So first we're going to prepare it. So preparing a recipe is akin to fitting our model. So to do this, we just need to provide, we're going to use a prep function, and we're going to provide the recipe that we've provided, that we specified, and then we're going to provide the training data set. So running this, we can see now that we have performed this recipe onto our data. So we have now applied it to our data set. We've applied it to this training data set. And then now we're ready to bake the recipe on, which can be seen as the same as predict. So we are ready to, we just provide our recipe imputed and prepped, and we're going to apply this to our training data. And doing so, we now have our training data imputed. So if we look at this, we can see now that we have centered and scaled all of our data, and yeah, we have imputed all the NA values. We can also now perform the same recipe on the test data. Now this is important. We are not, our recipe is not prepped on the test data, it's prepped on the training data. So we know this. We're not leaking any information from the test set into our training set. We are just applying we're baking this preparation onto this test set. We have not created this prep from our test set. And doing so, this will do a very similar as above to our test set. So great, so now we are ready to fit our model. And this is going to be done in very much a similar way as we did before. So again, we're specifying our logistic regression. we are setting our engine to GLM, and then we are specifying, we're going to call our fit, but this time we're going to set our data to be this our train imputed. And running that, we now have our model, which we can look at as so, with our coefficients. And this time we're going to, very much similar way, we're going to assess how well our model has done using these predictions. So we can bind our columns. We're going to bind firstly the actual cases, the target cases, what the actual values are, and then we're going to predict using this fitted model we've just created. We are going to compare this against our prepped test data set. And running this, we now have a second set of predictions. And so let's have a look at this. We can see that we have, again, our cases where malignant is being predicted. And you remember if earlier we had an NA value for row number 8, but because we have imputed our NA values during our recipe, we no longer have an NA value here, so the model has been able to predict that this is in fact a malignant value. So let's calculate some metrics again to compare how these models have performed. So I'm going to do exactly the same as I did before and say this in metric 2, met2. And we can see here that, okay, our accuracy is not 96% again, and our kappa is 92%. If we go back and look at our metrics from our first model, we can see that, okay, the accuracy hasn't changed, but the kappa is increased by a very, very small amount, but it's got better. So our recipe has now, our pre-processing has improved our model very slightly. And again, we could calculate the confusion matrix, and we could compare these values to our previous confusion matrix if we wanted to. And so that is pre-processing. That's a very brief touch on machine learning. There are many, many more steps to becoming a full being experienced in machine learning. If you are interested, Mango has a machine learning in R course, which covers some of the topics we've discussed so far, but many, many more, and in much more detail. So without further ado, I'd just like to thank you for attending this webinar. I hope you found it useful, and if you are interested in any further contact, then the contact details are listed below.